On July 4, 2012, the world of physics changed forever. After decades of work, scientists at CERN, using the Large Hadron Collider, announced the discovery of the Higgs boson, a particle theorized over 50 years earlier. This discovery was the missing piece of the standard model of particle physics, but it also opened new questions about the universe. To understand the significance of this discovery, we first need to know what the Higgs boson is and why it's so important. In the 1960s, physicists Peter Higgs, François Englert, and Robert Brout, among others, proposed the existence of an invisible field that fills all of space. This field, known as the Higgs field, interacts with subatomic particles, giving them mass. The Higgs field can be imagined as a kind of cosmic molasses. Imagine particles as little marbles moving through this field. The more they interact with the field, the more they slow down, which we interpret as mass. Particles like photons, which do not interact with the field, continue to move at the speed of light, and have no mass. The Higgs boson is the particle that represents fluctuations in this field. It is, in a sense, the confirmation that the Higgs field truly exists. Before the discovery of the Higgs boson, the theory explaining how particles gain mass was just that, a theory. While the standard model of particle physics has been incredibly successful in explaining most of the fundamental forces of the universe, electromagnetism, the weak interaction, and the strong interaction, it had a major gap. It couldn't conclusively explain why particles have mass. This is crucial because mass allows particles to come together, form atoms, molecules, and ultimately the universe as we know it. The Higgs field, proposed in the 1960s, offered an elegant theoretical solution. But for decades, there was no experimental evidence that this field existed, nor of the particle associated with it, the Higgs boson. The discovery in 2012 was the moment when theory became reality. Detecting the Higgs boson was no easy task. In fact, it was one of the greatest challenges in modern science. To find it, scientists had to build the Large Hadron Collider, the world's largest and most powerful particle accelerator, located in a 27-kilometer underground tunnel on the border between Switzerland and France. In the LHC, protons are accelerated to nearly the speed of light, and made to collide with each other at incredibly high energies. These collisions recreate the conditions that existed just after the Big Bang. From these collisions, subatomic particles emerge, some of which had never been seen before. Among these, the elusive Higgs boson was expected to be found. However, the Higgs boson is extremely unstable and only exists for a fraction of a second before decaying into other particles. The experiments at the LHC did not detect the Higgs boson directly but confirmed its existence by observing the patterns in which it decayed. The discovery of the Higgs boson is important for several reasons. First, it fills a crucial gap in the standard model. This theory, which describes all the fundamental particles and forces in the universe, except for gravity, has been experimentally confirmed time and again, and the Higgs boson was the last missing piece in this puzzle. But while the Higgs boson confirms the standard model, it also suggests that there is much more to discover. For example, the standard model doesn't explain gravity, nor phenomena like dark matter or dark energy, which make up 95% of the universe. Some scientists believe that the discovery of the Higgs boson could be the first step toward a new physics that explains these mysterious forces. Moreover, detecting the Higgs boson also has practical implications. Although we are still far from direct technological applications, understanding how particles gain mass could one day help us develop new technologies that we can't even imagine today. The discovery of the Higgs boson was not the end of the story but the beginning of a new era in physics. Now that we know the Higgs field exists, scientists are investigating its properties and searching for clues about phenomena that the standard model cannot explain, such as the nature of dark matter and why there is an imbalance between matter and antimatter in the universe. The Higgs boson is only the beginning of what could be a revolution in our understanding of the universe. As we move forward, experiments at the LHC and other particle accelerators could reveal new particles, new forces, and perhaps a more complete theory that brings us closer to understanding the deepest secrets of the cosmos.